All right, listen up. This isn't just another revision session. Think of this as your personal boot camp, a high-intensity drill designed to help you absolutely dominate AC circuits in your CBSE physics exam. We've gone through years of past papers, found all the patterns, and built a 15-question meta quiz that we're going to tackle right now, one by one. And here's the catch. The clock is always ticking. We're on a strict 90 seconds per mark, so let's get into it.
What if I told you that you could practically read the examiner's mind? Well, that's what we're doing today. We're decoding the exam, revealing the patterns that show up year after year after year. These are their favorite questions on impedance, phase, resonance, RMS values, and transformers. This is your cheat sheet based on pure data.
And if there's one number you need to burn into your brain, it's this one, 50%. A full half of all the questions you're likely to face will be on series LCR circuits. So let's be crystal clear. This is where the entire battle is won or lost. You get this right, and you are already halfway to an amazing score.
Okay, so here are the rules of engagement for this workout. We have our 15-question quiz. We're sticking to that 90 seconds per mark timing to build both your speed and your accuracy. We're only focusing on the stuff that comes up all the time. And a pro tip, always box your final answers. It just makes the examiner's job easier, and that's what you want.
So, here's our game plan. We're kicking things off with the heavy lifting, the big theory derivations. Then, we'll move into some real-world case studies. After that, a quick round of rapid-fire concepts to test your recall. Then, we'll crunch some numbers. And finally, we'll wrap up by proving we really get it, by explaining the why behind it all.
All right, let's do this. Round 1. This is all about locking in those huge 5-mark questions. These derivations are practically guaranteed to show up in some form, so mastering them is totally non-negotiable. Let's start. First up, the RMS value. For 5 marks, you always start with the definition. And here's the key idea you have to communicate. RMS is all about heat. It's the value of a steady, constant DC current that would generate the exact same amount of heat in a resistor as our fluctuating alternating current does.
So, how do we get there? The derivation is all about averaging the instantaneous current squared, that's I naught squared, times sine squared omega t over one full cycle. Now, here's the mathematical shortcut you have to remember. The average value of a sine squared function over a complete cycle is just 1/2. Simple as that. Take the square root of that mean value, and bam, you get the most important relationship here. IRMS is the peak current, I naught, divided by the square root of 2.
Okay, next 5-mark question, deriving impedance. You absolutely have to start this by sketching a phasor diagram, so picture it right now. Draw your current phasor I as a horizontal arrow pointing to the right. The resistor's voltage, VR, is in phase, so it points right too. Now, the inductor's voltage, VL, leads by 90 degrees, so it points straight up, and the capacitor's voltage, VC, lags by 90 degrees, so it points straight down.
So, with that diagram in your head, the net voltage from the inductor and capacitor is just VL minus VC, a vertical line. That vertical phasor, combined with the horizontal VR phasor, well, it forms a perfect right-angled triangle. The hypotenuse is just your total source voltage. A little bit of Pythagoras' theorem, you substitute in, V equals I times Z, VR equals I times R, and so on, cancel out the current from every term, and you're left with the impedance formula. Z equals the square root of R squared plus the square of XL minus XC.
Question 3, the transformer. To get full marks, you need to state the core principle right away. It works on mutual induction. The changing magnetic flux from the primary coil, it induces a voltage in the secondary coil. And for an ideal transformer, you have to state the key assumption. No energy is lost. That means the power going in, VPIP, has to equal the power coming out, VSIS.
So, how does that lead to the formula? Well, Faraday's law tells us the voltage in the primary is Np times d phi by dt, and in the secondary, it's Ns times d phi by dt. And here's the magic part. In an ideal transformer, that changing flux, the d phi by dt term, is exactly the same for both coils. So if you just divide one equation by the other, that term cancels out completely, leaving you with the famous turn ratio formula. The ratio of the voltages is exactly the same as the ratio of the turns.
All right, last big derivation, average power. We always start with the instantaneous expressions. So voltage is V naught sine omega t, and current is I naught sine of omega t plus phi, where phi is just that phase difference. The instantaneous power at any moment is simply the product of those two. To get the average, you guessed it, we have to integrate that whole messy product over one complete cycle.
Now, when you actually do that math, something really neat happens. All the messy parts, like the sine times cosine terms, they average out to 0 over a full cycle. The only part that survives gives us this beautiful result. The average power is 1/2 V0 I0 times cosine phi. And since we know VRMS is V0 over root 2, we can rewrite that in its final, most useful form, VRMS times IRMS times cosine phi. And that cosine term, that is the super important power factor.
Phew. Okay, that was the heavy lifting. Now let's move to round 2. This is where we take those formulas we just derived and use them to solve actual, practical circuit problems. It's all about applying the physics. Okay, here's a classic case study. You've got a light bulb in series with a capacitor. The question is, what happens to the bulb's brightness if you lower the AC frequency? You can't just give the answer, you have to show the chain of logic. Step 1. Capacitive reactance, Xc, is 1 over 2 pi Fc. So as frequency F goes down, Xc goes up. Step 2. The total impedance Z depends on Xc. As Xc increases, Z also has to increase. Step 3. Ohm's law. Current I is V over Z. As Z goes up, current I has to go down. And finally, step 4. The bulb's brightness depends on power, I squared R. Less current means a dimmer bulb. It's a perfect 4-step cause and effect chain. All right, time to pick up the pace. Let's jump into round 3, rapid-fire concepts. These are quick, 1-mark questions. They're all about your instant recall of the fundamentals. You ready? First question. In which of these pure components does the current lag behind the voltage by a full 90 degrees? Is it the resistor, the inductor, or the capacitor? Think fast.
The answer is B, the pure inductor. And here's the best memory aid ever, Eli the Iceman. For an inductor, L, voltage, E, comes before current, I. That's Eli. And for a capacitor, C, current, I, comes before voltage, E. That's ice. Works every time. Okay, rapid fire. What's the condition for resonance? XL equals XC. And in a pure resistor, current and voltage are perfectly in phase.
Time for round 4, the numbers game. Let's do a quick calculation. Let's say you need to find the capacitive reactance, Xc, for a 10 microfarad capacitor on a 50 Hz supply. First, you write down the formula, Xc equals 1 over 2 pi Fc. Then you plug in the numbers, but be careful. You have to convert 10 microfarads into 10 times 10 to the minus 6 farads. Punch that in and you get about 318 ohms. Remember the process, formula, substitution, then a nice boxed final answer with the units. That's how you get all the marks. And now we've arrived at our final and, in my opinion, the most important round of all, explaining why. See, this is what separates the students who get good marks from the ones who get great marks. It's not enough to just know the rule, you have to be able to explain the physics behind it. So let's ask why. Why does current lead in a capacitor but lag in an inductor? Well, for a capacitor, think about it physically. You have to push current onto the capacitor plates first in order to build up the charge, and that stored charge is the voltage, so the current has to come first. For an inductor, it's the opposite. An inductor resists change. It creates a back EMF, a voltage that opposes the change in current, so the voltage has to build up first to overcome that resistance, forcing the current to lag behind. That physical reasoning is what they're looking for. So as we wrap up this drill, let's run through our error elimination protocol one last time. Number 1, always use RMS values for power, unless they specifically tell you otherwise. 2, never mix up reactions, which is for a single component, and impedance for the whole circuit. 3, always double-check your units, microfarads to farads. 4, box that final answer. And 5, explain your reasoning. If you follow these 5 rules, you're going to maximize your score. And I want to leave you with this one core idea. The CBSE exam is not just a math test where you plug numbers into formulas. It is a communication test. Your job is to clearly and logically communicate your understanding of the physics to the person on the other side of that answer sheet. So, there it is. That's your battle plan. You've got the high-frequency patterns, you've got the formulas, and you've got the strategies. The only question left is, are you ready to make that final shift in your thinking? To go beyond just finding an answer and to start truly explaining the physics behind it? Because that right there is the real secret to success.